Myself, Dr.CR Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So today I am going to discuss about the upconversion of erbium-3+-doped oxyfluoride transparent glass ceramics containing transparent fluoride nanocrystal. This is one of the important topic from the laser glass spectroscopy. So last section and previous session we discussed on the synthesis of lanthanum-3+-doped transparent glass ceramics for photonic applications. In that we discussed about the introduction, importance of glass ceramics and the synthesis of lanthanum-3+-doped transparent glass ceramics and application of the transparent glass ceramics and the conclusion of summary of the lanthanum-3+-doped transparent glass ceramics. So outline of the today talk is on the upconversion of erbium-3+-doped oxyfluoride transparent glass ceramics containing strontium fluoride nanocrystals. In that we are going to discuss about the introduction of the erbium-3+-doped oxyfluoride transparent glass ceramics and experimental methods and techniques of the erbium-3+-doped oxyfluoride transparent glass ceramics containing strontium fluoride nanocrystals and resultant discussion of the erbium-3+-doped oxyfluoride glasses, and finally conclusion or summary of the erbium-3+-doped oxyfluoride transparent glass ceramics containing strontium fluoride nanocrystals, and also we will discuss in the mainly upconversion properties in the particularly transparent glass ceramics. So coming to the introduction, the main motivation of the rare earth elements or lanthanum ions in the modern periodic table. We are going to discuss over the different kind of elements here. In particular, we have discussed the rare earth dope or lanthanum 3+-dope glass ceramics. In that one, we are going to discuss about the among the 14 lanthanum elements. We are going to discuss about in this study erbium 3+ science. That is atomic number 68. That we are going to discuss about the black element. This is one of the important rare earth elements to doped with the transparent glass ceramics. So because it's enhance the luminescence properties and optical properties, and also we can discuss the upconversion studies also we can discuss in the particularly in the case of erbium 3+ rare earth elements. So that is why we are discussing the upconversion of erbium 3+-doped oxyfluoride transparent glass ceramics containing strontium fluoride nanocrystals. This is one of the important nanocrystals, strontium fluoride nanocrystals. That is we are going to discuss in this present study. So what is the main motivation of the lanthanum 3+ or rare 3+ ions? So in this particularly we are discussing the erbium 3+ ions. This incomplete inner of 4f-n orbitals. So mainly optical properties in the study of importance of lanthanum 3+ ions, strong absorption and fluorescence and wide range of excitation levels and emission levels, that is from the UV visible to infrared regions. So we can get the wide band of absorptions and luminescence from the UV visible to infrared region. So main application in the erbium 3+-doped and oxyfluoride transparent glass ceramics is the lasers, displays, sensors and lighting and biomedical imaging and extra different kind of applications we can use for the erbium 3+-doped oxyfluoride transparent glass. In particularly telecommunication and optical amplifier applications we are much using for the erbium 3+-doped glasses. These are the different emission analysis from the blue to NIR region. So this is thulium, terbium, dysprosium, europium, cerium. These are we are getting in this region of visible region. In the case of ytterbium, neodymium, erbium, we are getting the infrared region. That is near infrared and mid infrared and far infrared region. We can get the different kind of luminescence analysis from the ytterbium ion and Nd ion and erbium. Particularly erbium, we can get the NIR emission. That is why we are using for the telecommunication applications. We are using for the one of the important elements for the erbium 3+ elements. So what is the main introduction of the glass ceramic materials? So mainly glass ceramics is having the two-phase materials, that is crystalline and amorphous materials. Why the reason is to enhance the luminescence properties of rare earth elements, to increase the emission as well as decay time measurements. What are the main requirements to prepare the glass ceramic material? Is small crystal size, that is nano size. That is nano size material is required. In the particular in our case we are using the strontium fluoride nanocrystal we are using. The refractive index of crystalline phase, percentage of nanocrystal embedded in the glass matrix. That is the very important in the glass ceramics. So what are the special chemical composition what we are going to use in the present study? So oxyfluoride glasses with doped with lead fluoride, zinc fluoride, and barium fluoride, sodium fluoride, strontium fluoride, yttrium fluoride, calcium fluoride. So whenever this fluoride content will be present in the present chemical composition, so which is the very important to enhance the luminescence properties means what are the nanocrystal will be present in the glass matrix. So in our present study, we have studied the strontium fluoride nanocrystals. This is one of the important material to enhance the luminescence properties in the case of oxyfluoride glass materials. In oxide classes with the silicon dioxide, yttrium oxide, phosphorus pentoxide, germanium oxide, hafnium oxide. These are we are using for the oxide based glasses. In other glasses is fluoride glasses, completely fluoride glasses or chalcogen. Chalcogen glass is nothing but lead to sulfur. These are the toxic elements, and also we can preparation is very difficult, but you can prepare the chalcogen by using the melt quenching technique and different kind of methods to prepare the chalcogen glasses. So what are the methods to prepare the transparent glass ceramics? One is the important unique technique is called the heat treatment process or nucleation process. That is one of the important technique to prepare the glass material to glass ceramic materials. Next, other one is laser annealing. Also, we can prepare the transparent glass ceramics. And other one is the sol gel technology. Also, we can use to prepare the glass ceramic material from the glass material. So, what is the main introduction in particular in the glass ceramics? So, glass ceramics are polycrystalline ceramic materials formed through the controlled nucleation growth crystalline phase in precursor glass. That is a crystalline phase and precursor. That means we have two phase required. That is one is crystalline phase, other one is glassy phase. That is amorphous nature and crystalline nature. The glass ceramics is usually made in the two steps. First, the precursor glass is made by the normal melt quenching. First, initially we have to prepare the normal melt quenching technique. That is one of the important technique to prepare the amorphous material or glassy materials. After that, then a structure phase transition in thermally induced in the transform into the composition material formed by the at least one crystalline phase dispersed within the glassy matrix. So that glassy matrix it should be exhibit at least one crystalline phase. Then only we can prepare for the glass ceramics. Without a crystalline phase, we cannot prepare the glass ceramics from the glass materials. That is why we require at least one crystalline phase while preparing the glass ceramic material. That is one of the unique parameter. Next, the oxyfluoride glass ceramics doped with rare earth elements have been investigated widely in the past decades as they provide a desirable low phonon energy. That is fluoride environment. Whenever doping with fluoride content, it will reduce the phonon energy. Phonon energy, that means vibration energy will be reduced from high to low. That is why we are adding the fluoride content in the active rare earth ions while maintaining the advantage of oxide glasses such as high mechanical strength, chemical durability, and thermal stability will be increases. Whenever doping with the fluoride content, automatically phonon energy will be decreasing. It decreasing means we have to enhance the luminescence properties. At the same time, in oxide-based glasses, high mechanical strength, chemical durability, and thermal strength will be increasing in the oxyfluoride glass ceramics. Next, in oxyfluoride glasses doped with erbium doped transparent glass ceramics are widely very much useful for the increasing the efficiency of solar cell because of inhomogeneous broadening in absorption spectrum. In this erbium doped transparent glass ceramics, we can use for the solar cell applications also because it absorbs the inhomogeneous broadening in the absorption spectrum of erbium 3 plus ions due to the disorder of host, which allows the absorption of larger part of the solar spectrum. So we can observe the solar spectrum, that is silicon band gap is 1.1 electron volt. That is silicon band gap is 1.1 electron volt. But in the case of erbium 3 plus doped transparent glass ceramics, we can observe around 1.1 electron volt of energy will be you can observing the absorption spectrum. That is why it will be inhomogeneous broadening in the absorption spectra of erbium 3 plus ions due to disorder of the host material, which allows absorption of the larger part of the solar spectrum. So it can cover the larger spectrum of the solar spectrum while doping with erbium 3 plus doped transparent glass ceramics. These are the one of the important property in the glass ceramics. Next, what are the importance of glass ceramics compared to the amorphous materials? See the exhibit better thermal stability. That is one of the important technique. Next, superior electrical insulation. That is one of the important parameter. Next, higher chemical strength. This is also one of the important parameter. Next, thermal expansion coefficient tunability also it will be shows the very essential to the prepare the glass ceramics. Next, enhancement of luminescence properties. This is the finally So we are going to prepare the glass ceramics to enhance increase the luminescence properties as well as optical properties, and also upconversion properties also we can enhance by using the glass ceramic material. So that is why glass ceramics are the important system to prepare the enhancement of the optical and luminescence properties as well as decay time also. That is why these are the important parameter in the glass ceramic materials. Next, lanthanum 3 plus dope transparent glass ceramics. So we have to prepare the transparent glass ceramics. If we prepare the glass ceramics, we need the at least one glassy phase nature and one crystal phase nature. This is processed by the controlled nucleation and crystallization of the crystal phase in a precursor glass. So precursor glass, at least it shows the at least one crystalline phase. Then only we can prepare the glass ceramic material. So this oxyfluoride transparent glass ceramics, they are doped with the different rare earth elements. Say optical properties of rare earth ions in fluoride host. So particularly in the optical materials, whenever doped with the rare earth ions, at least you require the fluoride content, that is calcium fluoride or barium fluoride or calcium fluoride, or different kind of fluoride content should be there. Then only it will be, a nanocrystal will be formed. Automatically it enhances the luminescence property. So there is a macroscopic properties of aluminum silicate glass. Particularly aluminum silicate glasses is mainly one of the important host material to prepare the glass ceramics. That will be in macroscopic bulk material too. We can prepare the nano size nanocrystals. That is why this is useful for the macroscopic properties of aluminum silicate glasses. These are the important things for the transparent glass ceramics. So oxyfluoride transparent glass ceramics, particularly this is the same diagram. So in this nanocrystals, if 25% of volume, we can get the 10 to 25 nanometer size. So if this is big circles, it shows the oxyfluoride content system, glassy matrix. In that one, this is in big circle, this is fluoride nanocrystal. In that red one is the rare earth elements. In particularly 80% of nanocrystal, in 15% of glassy matrix, it will be occupied in the glassy matrix. So that is why. So this rare earth elements sit into the fluoride nanocrystal. Automatically, whenever the nanocrystal will be sitting the rare earth elements, so automatically luminescence property will be enhanced. That means that refractive index will be changing. So that is very important parameter to enhance the luminescence properties. At the same time, photon energy will be decreasing. That is, inside the oxyfluoride glasses having the photon energy will be in around 800 900 centimeters. Whenever that fluoride content will be formed inside the glassy matter, that means transition. In the case of here, transition fluoride content will be formed inside the glassy oxyfluoride nanocrystals. So automatically that photon energy will be decreasing less than 300 centimeters. That is why it enhances the luminescence properties as well as decay time measurements. These are the oxyfluoride transparent glass ceramics. Next, coming to the what is meant by upconversion. So photo excitation is a certain wavelength of near infrared followed by the luminescence at a shorter wavelength in the visible is called the upconversion. That is a IR to visible photon frequency upconversion. That is, you can say frequency upconversion. That means upconversion is nothing but we are giving the low energy, but you are getting the output. Input energy will be we are pumping with low energy, but output we are getting is higher energy. So that is the main parameter to get the upconversion property. See here, we are two photons we are pumping, but we are getting one photon of the higher energy, blue emission we are observing. See here, two photons we are pumping and we are getting one blue emission. So this is called the upconversion process. Upconversion is nothing but we are pumping energy will be very low and we are getting output energy will be very high. So this is the process is called the upconversion process. That means that is the IR to visible photon frequency upconversion. IR means IR infrared region wavelength will be high. At the same time, energy will be low. The visible wavelength is very low. At the same time, its energy will be more. That is why we are using IR to visible photon frequency of conversion. This is the excited state absorption. Yes, excited state of conversion. See, this is two hands process in the energy level diagram that we are going to discuss in the energy level diagram. So, how to prepare the glass material first? Initially, you have to prepare the glass material. Then after that, we can that nucleation process or heating process, we can prepare the glass material to glass ceramics. In particularly in this study, we use the erbium 3+ dope oxyfluoride glass for the composition is silicon dioxide, 41 mole percent of silicon dioxide and 10 mole percent of aluminum oxide and 24% of lithium fluoride and 23 mole percent of strontium fluoride and 2 mole percent of impurity, that is erbium 3 plus is 2 mole percentage of Er2, the erbium oxide. So in this particularly we are 24 mole and 23 mole percent of fluoride content we are using lithium fluoride as well as strontium fluoride. In this composition we are using more mole percentage of fluoride content. That is why this automatically this complete composition material we can reduce the fluoride energy because fluoride content will be more in this composition. That is why it reduces the fluoride energy band from 900 centimeter inverse to 300 centimeter inverse. So, and also it form the strontium fluoride nanocrystal, in particular the Fe3+dopedoxyfluoride glasses. So, these are the preparation of glass materials. So, after preparing the glass material, we are sent for the DT analysis. After preparation of the glass materials, we are sent the DT analysis. That means differential thermal analysis technique. We can measure the DT analysis. In DT analysis, we are measuring the glass transition temperature, crystalline temperature C1 and C2. These are the crystalline temperature, and Tm is the melting temperature of the particularly glass material. Which glass material we are prepared? That glass material we have to first we need to characterize the DT analysis. By using the DT analysis, we can get the TC value, TC1 and TC2. That means glass transition temperature, crystalline temperature and melting temperature. By using the, so if we prepare the amorphous material to ceramic material, glass ceramics, we need particularly one crystalline phase. So we need one crystalline temperature value. So that we are getting from the DT analysis. By using DT analysis, we are prepare the glass ceramic. That is glasses prepared by the melt quenching technique and annealing. Next, controlled crystallization base glass. We have to prepare the that parent glass means that is a glass material. We need to control crystallization of base glass. That base glass we prepare the DT analysis taking. But what is the crystalline temperature? In particular temperature, we need to do the nucleation process to prepare the this is heat schedule for conversion of glass to glass ceramics. This is diagram. This is time versus temperature. So what temperature we are keeping the nucleation process? Particularly in the case of erbium-3+, we are using 480 degrees centigrade. At that time, how much hours we are keeping? Then how glass material will be converted into glass ceramics. That is the preparation of the glass ceramics. So what are the experimental technique and methods characterization? So first initially differential thermal analysis, that DTA measurements is characterized by using the STQQ 600 V8.3 bold 101 differential thermal analyzer. That is model is Newcastle DE. This is purchased by the Newcastle DE. Next, X-ray diffraction. XRD is recorded with a X-ray diffractometer. Smart Lab Rigaku, that is from Tokyo, Japan, using the copper K alpha radiation. This is K alpha radiation. K alpha radiation. Next, transition electron TEM analysis were recorded in GL TEM 2010. This is also purchased from the Japan company with an accelerating voltage of 200 kilovolt. So this is the TEM analysis. Next, absorption spectrum analysis is analyzed by the Perkin-Elmer spectrophotometer. That is spectrometer model is lambda 950 in the wavelength range from 300 nanometer to 2200 nanometer. Next, Stokes means down conversion emission and up conversion emissions and decay time spectra were recorded with a monochromator DK240 having a PMT means photo multiplier 2 exciting at 365 nanometer light emitting diode is LED and 980 nanometer LD, that means light diode respectively. Decay curves of the Fortress 3x2 level of erbium-3+ science were measured using digital storage oscilloscope, that is Flickr 9310A, that is in New York, pumped by the third harmonic 355 nanometer of a ND-YAG laser spectrophysics lab. That is used for the upconversion process. In upconversion process, they are used for the neodymium YAG laser spectra. By using, we are getting the upconversion analysis and lifetime measurements we are observed by using this spectrophotometer. Next, all the measurements were carried out at room temperature only. So these are the DT analysis. First, initially you need to measure DT analysis first. Next, XRD analysis. Next, TEM analysis. Next, absorption and luminescence properties is Stokes emission means down conversion and up conversion emission, and also lifetime measurements or decay time measurements we have carried out by using this instruments. So all the measurements were carried out at room temperature only. Next, first initially we need to measure the DTA analysis. That is, this is the spectra for the DTA spectra, that is temperature versus temperature difference or degree centigrade. See here the 400 degree centigrade to 900 degree centigrade temperature, we are analyze the DTA analysis. We are getting here one is TG, that means 480 degree TG, that is glass transition temperature below 480 degree centigrade, and TX1, TX2, these are the both crystalline temperatures. 600 degree, first crystalline temperature at 600 degree centigrade, and second one is 730 degree centigrade. So both we are observing. So in particularly we are observing two crystalline temperatures. Based on two crystalline temperatures, we need to optimize the which crystalline phase we need to do the nucleation process or heating process to prepare the glass material to glass ceramics. See here in figure shows the DTA curve of the present glass, TG and crystalline temperatures values for glass transition, first and second crystallization temperature respectively. The first crystallization peak TX1 is observed for the precipitation of transparent fluoride nanocrystals, and the second crystallization peak TX2 is a bulk crystallization process of the glass matrix. So here in two crystalline phases, where this is one is the transparent fluoride nanocrystal phase, other one is bulk crystalline phase. So that is why we are using first crystalline phase TX1 600 degree centigrade. So we have use the nucleation process or heat treatment process, prepare the glass to glass ceramics. We are use the nucleation process at the temperature of 600 degrees centigrade. This is the optimized temperature to do the transfer from nanocrystal, particularly glass materials. So after that, we need to measure the XRD profile. The XRD profile, you see this is completely glass material, shows the broad diffraction peak. So this shows this completely prepared glass sample shows the glassy nature. After glass ceramics, we are 600 degrees centigrade, particularly glass ceramics. In 600 degrees centigrade, we are used for 2 hours, that is GC 2 hours, and GC 4 hours, and GC 6 hours. So each sample at a particularly crystalline phase, 600 degrees centigrade, we are nucleation process did at 2 hours, 600 degrees centigrade. Next, 4 hours and 6 hours. So in 2 hours, 4 hours, 6 hours, we are observing the transparent fluoride cubic structure, transparent fluoride nanocrystal cubic structure. We are observing in XRD profile. See this XRD profile, and particularly with a more intense peak for the glass ceramics at a 6 hour sample, indicating its higher crystallization nature and large size of the nanocrystal form. So this is the matching with the JCPDS card number 060262. This is well matched with the cubic structure of a transparent fluoride nanocrystal while preparing the R3+dopedoxyfluoride glass ceramics, transparent glass ceramics containing transparent fluoride nanocrystals. So in present glass, it shows the well matches with the transparent fluoride cubic structure. Particularly in 6 hours of glass ceramics, it shows the all the intense peaks shows the transparent fluoride nanocrystal phase. That is why the prepared sample shows the transparent fluoride nanocrystal. See, analysis of the peaks reveals that the sample contains a cubic transparent fluoride crystalline phase with a JCPDS standard card number is 060262. So well matches with the transparent fluoride nanocrystals. So that is why we are preparing the XRD profile by using the transparent fluoride nanocrystals. Next, coming to the XRD profile only, you need to measure by using the scalar equation, we need to evaluate what is the crystalline size. So from peak width of the XRD spectra, average size of the nanocrystal we need to measure by using the formula. HKL means lattice parameters of the nanocrystals, the K lambda B crystal. Here, where DHKL is the crystal size in vertical direction of HKL lattice parameters. Lambda is the wavelength of the X-rays, the X-ray luminescence, that is the lambda wavelength. Theta is the angle of diffraction. Next, beta is the full width of maximum of the diffraction peak, and diffraction peak at K value is 0.90, constant value. So by using these constant values, substituting the formula, we can get the crystal size of the transparent fluoride nanocrystals. In the particular study, the average size of the nanocrystal have been determined by using the XRD profile. We are getting the 35, 39, 40 nanometers crystal size of the transparent fluoride nanocrystals for the glass ceramics. 2 hours. So 2 hours means that is 600 degrees centigrade. Where nucleation process did that duration is 2 hours. Next glass ceramics 4 hours and 6 hours. So 6 hours we are getting the more particle nano size will be 40 nanometers. So 35, 39, 40. These are the average crystal size of the prepared glass ceramics in the Er3+ dope oxyfluoride glass transparent glass ceramics. So this nanocrystal are reported in the erbium co-dope glass ceramics. So same crystal size will be reported in the earlier reported in the erbium 3+ and yttrium 3+ co-dope glass ceramics. This also we are getting the almost nearly 40 nanometer average size of the nanocrystal we are observing in the other report also. So this is the TEM analysis. TEM analysis by using the strontium fluoride nanocrystal in TEM analysis, TEM micrograph of 2 mole percentage of erbium 3+ dope glass ceramics 6 hour sample. The insert shows the SAD pattern. That means the selected area electron diffraction pattern also we are observed by using the TEM analysis. In TEM analysis, that is XID analysis, we are observing the nanoparticle size, that is around average particle size is 35 to 40 nanometer. In TEM analysis also, we are getting the almost similar, that is a few particles shows the nano size ellipse-like morphology with an average particle size will be 40 nanometer. Whereas in XRD pattern, in XRD we are getting 35 to 40 nanometer, but in TEM analysis we are getting 40 nanometer. Average particle size will be 40 nanometer. So well correlated with the XRD and TEM analysis. So these are the selected area diffraction also pattern shows the concentric rings indicating polycrystalline nature of the glass ceramics, and it's shown in insert figure. All diffraction rings can be identified as cubic structure and is constant with the XRD pattern. So all the pattern will be concentric rings we can observe in the SAD pattern in the TEM analysis. So this shows the all the prepared strontium fluoride nanocrystal will be shows the cubic structure and is considered with the XRD pattern. So this is the TEM analysis. We are observing the nanoparticle size that is well coincided with XRD analysis. Next, absorption spectral analysis. From the absorption spectral analysis, first this shows the 13 absorption peaks are observed in the erbium 3+ dope oxyfluoride transparent glass ceramics. This glass we are showing 13. See, this is 2 hours glass ceramics, 4 hours glass ceramics, 6 hours glass ceramics. Particularly glass ceramics in 6 hours, we are going to see the here the band's intensity will be see this band. This is in the near infrared region. This is 1500 nanometer band with 13 band. That is 13 band is quartile 13/2 transition. That is assigned to quartile 13/2 excitation from ground state to ground state of the erbium 3+ ions is 15/2 quartile 13/2 transition. This transition, see the glass ceramics intensity will be very low. In the 2 hours will be increasing, and see the 4 hours in here. And if you see the 6 hours, it will be completely omitted. That means we not observe in the band is at the particularly in the case of glass ceramic 4 hours, that's absorption band will be increases. See here in the present glass ceramics 2 hours and 4 hours are fully transparent, but in the that means transparency means you can observe the high intensity of the NIR region in absorption spectra. But in the case of glass ceramics in 6 hours, completely it will be omitted. That means that decrease in the transparency might be due to the light scattering of large nanocrystals. So in this case, 6 hours, the nanocrystals formed very high nanocrystals. That is that due to the light scattering of larger nanocrystals. According to Rayleigh-Gans model, transparent glass ceramics can be obtained in the radiant nanocrystals less than 50 nanometer. If we do the transparent nanocrystals whenever formed in the glassy matrix, the radius of the nanocrystal should be less than 50 nanometer. The glass and glass ceramics, the variation, refractive index variation should be in the order of 50 nanometer, and the refractive index difference should be in the 0.1. The nanometer radius as well as that refractive index should be very varying. That is, it should be in the 0.1 in the refractive index, and the nanocrystal radius should be in the 50 nanometer difference. So this is shows the Rayleigh-Gans model. So well prepared the glass ceramics will be in the nanocrystals formation. In the parent glass ceramics, the size of the strontium fluoride nanocrystals increases gradually with increase of time thermal treatment, resulting in a gradual decrease in the transparency. So while increasing the temperature 2 hours, 4 hours, okay. After 6 hours, it will be completely opaque nature. That means completely ceramics, not transparent glass ceramics. So if you increase again more means it will be completely, it will be transparent, will be loses. That means completely it will show the opaque or turbid nature. That is why we need particularly up to 4 hours only. It shows the highly transparent compared to the UV visible to near infrared region. 300 nanometer to 1800 nanometer, it shows the highly transparent up to glass ceramics 4 hours. If you go for the 6 hours, it will be transparency will be decreasing. That is due to the scattering effect. That is light scattering of larger nanocrystals. So this is the absorption spectra. We are observing this information in the absorption spectra. So from using the absorption spectra only, we have calculated the JO intensity parameters, JO parameters, that is omega 2, omega 4, omega 6, and also susceptibility omega 4 by, that is spectroscopic quality factor value, that is omega 4 by omega 6. Next, what kind of trend is observed in the glass and glass ceramics. So omega 2 value in the glass ceramics, it shows the 7.16 in 10 power minus 20 centimeters square, and omega 4 is 1.51 into 10 power minus 20 centimeters square. Omega 6 is 2.34 10 power minus 20 centimeters. So here omega 2 value is more compared to omega 4 and omega 6. That is shows the magnitude of the JO parameter, and the evaluating JO parameters in the present work increases in the order of omega 2, omega 6 and omega 4. So omega 2 shows the higher value. That is why it's exhibit the covalent nature and asymmetry nature in the around the 3 parameters of the erbium-3+dope oxyfluoride transparent glass ceramics contained transparent fluoride nanocrystals. So next, this is the Stokes emission spectra, that is down conversion or normal emission spectra of the erbium-3+dope oxyfluoride glass ceramics. In this one emission spectra, we are observing the wavelength versus intensity 500 nanometer to 900 nanometer. We are scanning the luminescence spectra in that pumping with 365 nanometer and erbium-3+ the glass and glass ceramics. See the here emission intensity, see the glass material. This is black one shows the glass material. Remaining are the glass ceramics. Glass 2 hours, 4 hours and 6 hours. See the glass ceramics intensity will be very less when compared to glass ceramics. See, increasing the 2 hours, 4 hours, 6 hours. Almost luminescence intensity will be enhancing. That is mainly due to the, so we are observing 3 emission bands, one at 545 nanometer in the green emission and 626 in red emission. Other one is the 824 near infrared region. So these 3 emissions, particularly in the red emission, will be intensity will be enhancing will be very high compared to near infrared emission. See, green and red emission will be enhancing. So all the glass ceramics shows the not only the enhanced green emission from the quarters 3/2 level, but also more than 10 times stronger red emission from the quarter of 9/2. So red emission will be more than 10 times will be enhancement if takes place, and also near infrared emission from the quarter 9/2 level because of the reduced multiphonon relaxation. That is MPR means multiphonon relaxation. It implies that erbium-3+ are incorporated into transparent fluoride nanocrystals with lower phonon energy environment during the crystallization process. That means that phonon energy will be very less. That is why luminescence enhancement will be takes place. That is, phonon energy will be decreasing from 900 centimeter inverse to 300 centimeter inverse. That is why that is a multiphonon relaxation. That is why enhancement takes place in particularly in the green emission and red emission. This is the Stokes emission spectra from the erbium-3+dope oxyfluoride transparent glass ceramics. Next, this is the upconversion emission spectra. See the upconversion emission spectra of the glass material and glass ceramics. See the glass material shows the there is a upconversion luminescence will be highly negligible. If see the glass ceramics 2 hours, 4 hours and 6 hours increasing, and 6 hours of glass ceramics will be luminescence intensity will be enhancement will be very high. That is compared to glass materials. So this is the upconversion process. We are pumping with 980 nanometer. There is a 980 nanometer. We are pumping energy. That means 2 photon we are pumping, and we are getting single photon of the luminescence will be you are observing. At the particularly the red emission is the 650 nanometers. So this is the this plot for the pump power, how much pump power you are using and what are the pump intensity, how much intensity you are observing in the case of 545 with the green emission and red emission at 664 nanometer. So green emission at 545 nanometer, we are getting slope value. This we are fitting with the linear fit, we are getting the slope value is 1.338 and our red emission is 1.9. So red emission will be almost 2 photon. That is why you are getting this 2 photon pumping system. So that is we are by using this plot we can confirm with the this is the 2 photon upconversion we observed and single photon we are observed. That is upconversion is nothing but a down conversion and upconversion. Upconversion is mainly 2 photon pumping and single photon you are observing output power. So that is this is mainly carry with 1.9. That means around slope value we are getting is 2 photon. So 2 photon absorption takes place in the upconversion emission spectra. So next finally decay time measurements. The decay and the fluorescence decay time measurements in the erbium-3+ doped glass and glass ceramics. We are comparing glass and glass ceramics. We are pumping with 355 nanometer and emission mounted at 552 nanometers by using the ND-YAG laser at the emission mounted at the green emission 552 nanometer. We are pumping neodymium YAG laser, that is 355 nanometer. By using this neodymium YAG laser, we are getting the decay times for particularly in the glass having the average lifetime tau experimental value is 1.1 microseconds in the case of glass. In the case of glass ceramic material, that is 11.6, 10 times enhancement which takes place in the glass and glass ceramics. So glass showing the 1.1 microsecond only. In the case of glass ceramics is 6 hours, that is 11.6 microseconds we are observing. That means lifetime also enhanced more than 10 times, and particularly in the case of green emission, that is 550 nanometer. So tau excremental calculated by using this formula. So this results clearly indicate that the incorporation of erbium-3+ into transparent chloride nanocrystal in the glass ceramic sample resulting in the longer lifetime of the quarters 3/2 level. The green level, that is quarters 3/2 level is green emission 552 nanometer emission. We are observing the decay time measurements, and the decay lifetime will be 11.6 microseconds in the glass ceramic material. So this is the upconversion and lifetime measurements in the particularly in the erbium-3+ dopedoxyfluoride transparent glass ceramics. Yes, this is the energy level diagram of erbium-3+ dopedoxyfluoride glass ceramics, glass and glass ceramics. See here, we are pumping with 980 nanometer. This is ground state absorption, and this is non-reactive decay, and excited state absorption and excited state absorption 1 and 2. In this again non-reactive decay takes place and upconversion. Energy transfer through upconversion 1 and upconversion 2. These levels we are observing the 3 emissions, that is 546 nanometer in green emission, and 664 nanometer in red emission, and 828 nanometer in the near infrared region emissions. So these 3 emissions we are observing the down conversion as well as upconversion. Particularly in upconversion, we are enhancement luminescence will be observing more in the green emission and red emission. If compared to green emission, the red emission is the stronger upconversion emission, that will be 10 times more than the green emission. That is why this is useful for the upconversion emission in the case of erbium-3+ dopedoxyfluoride transparent glass ceramics. This figure shows the different emission channels. What are the excited state absorption? What are the excited state upconversion levels? So by using this energy level diagram, we can know the what kind of. See here, this is the pump photons through the process of knowing the excited state absorption ESA due to the good energy matching. So whenever this energy levels will be well matching, we can get the highly luminescence intensities. So these are the partial energy level diagram of erbium-3+ dopedoxyfluoride transparent glass ceramics. So finally, conclusion or summary. In particularly, erbium-3+ doped transparent oxyfluoride glass ceramics containing silicon fluoride nanocrystals have been prepared, and their optical luminescence properties were characterized. So we have characterized the optical properties, that is the absorption spectra and Stokes emission and down conversion and up conversion properties were characterized. Next, omega and the JO parameter gradually decreases from the glass to glass ceramics. That is mainly shows the intensity of both Stokes and upconversion emissions increases significantly with increase the time of thermal treatment of the glass material. So particularly in the glass ceramics, the luminescence emission will be upconversion emission and downconversion emission also increases gradually from glass to glass ceramics. Yes, the mechanism of upconversion emission is found to be two photon process. So we are getting the high pump and high intensity. That is a two photon. Almost the rate emission will be matches is 1.98. That is why the almost two photon process we observed in the upconversion mechanism will be found to be a two photon process. And lifetime of the green level, portrays 3/2 level, that is 552 nanometer emission, we are observing the glass ceramics found to be 10 times higher than that of the glass due to the lower Fresnel energy of the strontium fluoride nanocrystal surrounded the erbium 3 plus ions in the glass ceramics. That is why you are in estimate of the luminescence as well as lifetime measurements. That is mainly due to the low Fresnel energy of the strontium fluoride nanocrystals. Yes, the above results clearly indicate that the erbium 3 plus ions are progressively incorporated into strontium fluoride nanocrystal with increase in time of thermal treatment and the crystallization temperature of the glass material. So these are the main important points in the conclusion or summary of the present study of conversion of erbium 3 plus doped oxyfluoride transparent glass ceramics containing strontium fluoride nanocrystals. So these are the references used in the present work. So these are the introduction we have covered this. So this paper, this same work published in the Journal of Material Research in the year of 2013. So in this paper, we have studied the upconversion of erbium 3 plus doped oxyfluoride transparent glass ceramics. Mainly, this is useful for the erbium amplifier applications and telecommunication purpose. Even though at particularly 1.1 electron volt will be well matches with erbium 3 plus absorption spectra. That is why it can, this material also useful for the solar cell applications. Also, we can use for the this erbium 3 plus doped oxyfluoride transparent glass ceramics. So thank you. Next class will be continuing in the next session. Once again, thank you.
Like, share and subscribe. Hit the bell icon for more updates.